All right, so we are live, lecture 33. To bring in the discussion we were having right before class, so we were talking about unit conversions for the beam formulas, the moment shear deflection, particularly the deflection formulas that are in table 323, I think it is. You can convert the length to inches, like the beam length to inches, and you can do that and not have to use the 1728. And that will work only if you also convert any distributed loads to kips per inch. So you can go through and ignore the 1728. Those formulas are blind to units. They're not unit specific. They don't care about that. So you can do it one of two ways. You can use customary units that we've been using and throw a conversion factor in, or you can keep everything consistent. Just everything has to be consistent. All right, so let's just have a little bit of housekeeping before we get into beam design. So homework 6.2 is due today. Hopefully the hint that I provided or the little video I recorded after lecture, if you saw, I posted that on the playlist that had some hints for navigating homework 6.2. I believe I also posted that on Teams. Hopefully that helped. Also, I wanted to provide just sort of a summary of where we at on grading. Everything's graded up other than 6.1, so all of the column assignments are graded. All of the homeworks are graded today. And the one thing I don't think I had posted yet was the homework solution 6.1. But I'm going to go ahead and turn that on actually right now so that I remember and make available. So homework 6.1 solution is available. I don't think it's graded yet. I checked this morning and it hadn't been graded. But other than that, we're caught up. And all the attendance grades are up to date as of today. Let me check and see. Yeah, homework 6.1 still being graded. Like I said, we're going to keep on trucking with the assignments, so you get homework 6.3 today. I think it's maybe a little shorter than homework 6.2. That one was probably pretty long, not for the steel design side of things, but for the structural analysis side of things. And I really want to make sure that you're familiar with some of that and that you're comfortable with some of that, because our next topic is going to be discretely braced beams. And one of the more challenging aspects of discretely braced beams is the computation of a parameter called CB. And CB is going to be the focus of our next lecture, and it requires some structural analysis. So I just want to make sure that you're comfortable with that. Before we get into lecture, I just wanted to mention one final thing. I wanted to highlight a section of Engineering 350, which is being offered over the summer. You all probably haven't heard of that. Engineering 350 is it's part of a program that the college is implementing to try and document co-op experiences that students have had over the summer. It will document it on your transcripts. And better yet, the course really isn't for credit. It's really just a means of ensuring that any co-op experience that you've had, you get credit on your transcript. So it actually doesn't even cost any money to register for that class. Tanner Drown, who's our college co-op coordinator, his email address is drown12@Marshall. If you have a co-op experience and you're interested in that, I would send him an email. He's really helpful, and he'll talk you through the process. It's worth considering it if you've got a co-op experience over the summer. Okay, so let's get into beams. I want to start with table 3.2 because table 3.2 is the really where design starts. And even for discretely braced beams, table 3.2 is going to be a very valuable aid to us. Now, keep in mind that table 3.2 is written based off of an FY of 50 KSI. We can still use this table for continuously braced beam design. For discretely braced beam design, if we had a section that wasn't 50 KSI steel, we'd probably have a couple issues because the way the table is written, it's like the FEMR, the BF, the LP and LR, all that stuff. We'd have to tweak that a bit. But you know, we're going to be using 50 KSI steel for most W sections anyway, so it's not that big of a concern. We can use table 3.2 to just straight up look up the capacity. We don't even really need to compute it, because and that's for a continuously braced beam, because for a continuously braced beam, the nominal moment capacity is just MP, and they're right there. Now, Mr. Romans asked a very poignant question last time. He said that what's the deal with the sections that are bolded, okay? Well, if you open that table, you're going to find that the sections are grouped in sort of clusters, and there might be, you know, for instance, 5 sections in a cluster, or 2, or 7, or whatever. And within each of those clusters, the top row is bolded, okay? And if you look at each cluster, what you will find is that the top row is bolded because within that cluster, that is the lightest section. So for example, if I look at, I need to turn my highlighter on, turn that back to red and then turn my highlighter on. If I look at, let's say, this cluster right here, okay? If I look at that, I have, what do I have? I've got a W18 by 71. I've got a W10 by 112. Remember, that second number tells you how heavy it is, 96, 77. And then a W24 by 62. Of those 5 sections, the W24 by 62 is the lightest, okay? So if I'm in design land, what I can do is I can solve for the required moment, go to this column if it's a continuously braced beam. So let's say I have, for example, let's put some numbers to this. Let's say I have MU is 550 foot kips, okay? I can go to this table and I could select a W10 by 112 because it has a moment capacity of 551. From an efficiency standpoint, if I'm looking at MU over FMN, that's a pretty efficient section. I will grant you that. But why would I select a W10 by 112 when I could select a W14 by 62? A W24 by 62. The W24 by 62 is a lot lighter and a lot cheaper. Those bold rows sometimes are called economy sections. And so if you ever hear that term economy sections, those are the sort of the sweet spot shapes, if you will, that guarantee economy. Now, there is a reason why you would go with maybe one of these other sections. And I want to put the real world spin on this so that you're aware. When you look at these groups, for example, if we go back to this group, the upper row is the lightest shape. That is true. But sometimes what can also happen is that upper row might also be the deepest. And so you might also have issues with architectural constraints. For instance, if I'm designing the beams that support the floors in this building, I have to be able to fit my beam in between the space between the drop ceiling and then, you know, the floor above. So I might not have a lot of space to fit that beam in. And so maybe a W24 by 62 is the most economical section, but then the architect says, I don't have 24 inches to put a beam in. I only have 18. And so maybe then I go with, I don't know, the 18 by 71 or something like that, or the 16 by 77. Even though it's not as efficient, it meets the real world constraints, okay? Does that kind of make sense from a process standpoint? And does anybody have any questions about that? I'm going to take that as a yes. Now, okay. Now, I want to introduce you also to a new table, which is table 3-3. Okay, table 3-3 is obviously the one right next to the ZX tables, and so this is the IX tables. This is the IX table. The IX table, it looks a little bit like the ZX tables and how the grouping is, but really all it is just a bunch of sections listed, sorted by their IX values. So it's basically all the W shapes in the manual sorted by IX, and anytime there's a light section, they group it, and then that top row is bolded. See, the reason for this table is, you know, as we found out in our previous example, sometimes the strength limit state is not the one that matters. Sometimes it's the deflection limit state. So I'll sort of put some numbers to you so you can kind of understand what I'm talking about here. Let me go back to a previous example that we did last time, let's go back to some of the calculations we did last time. So I'm going to pull up my previous example once I can find my mouse pointer here. So this was an example that we did last time, and we were looking at moment shear and deflection for a representative beam. Now I'm going to introduce you to some bridge engineering terminology, and I'm going to introduce you to what's called a performance ratio. We've already done performance ratios sort of before when we looked at efficiencies. We looked at PU over VPN, and so I kind of want to use that to illustrate what's going on with this problem. So I'm going to cheat a little bit. I'm going to copy this and copy this down here just to sort of indicate what's going on here. So let me zoom kind of like this. Okay, that's good. Okay, so if I wanted to compute, for example, a performance ratio, hold on, that didn't write. Hold on, eraser. Why is that not liking me? What is going on here? My pen is not liking me right now. I'm getting a little worried about that. Sorry, bear with me. I'm sorry. Okay, let's try this. All right. Sorry about that. If I wanted to compute a performance ratio, let's say for moment, what I would do is I would take mu over phi mn. So I would take, 470.3 over 540, and I would get, 470.3 divided by 540. I would get 0.871. If I wanted to do one for shear, I would do, 58.8 over 252, and I'd get 0.233. And the nice thing about performance ratios is I can do it really for any limit. I could also do performance ratios for deflection. And so I might say, my maximum deflection divided by my limit. And so I might say 0.92 divided by 0.96. And so this is going to give me 0.958. Okay. The nice thing about a performance ratio is it allows an engineer to sort of look at the problem in a normalized fashion, and you can start to see what governs the design. For instance, if I look at these three performance ratios for moment, shear, and deflection, you can look at this and see that shear really didn't matter for this particular beam. If I look at the shear load versus the shear capacity, there's more than enough capacity. The performance ratio is really small. For moment, moment mattered a lot more, but it didn't matter as much as deflection. For this particular problem, deflection is what governed the design. That's why whenever I say the term governed, this is sort of what I mean. This is another way of looking at it. And that was the case for this beam. For another beam, that might not be the case. We might have a performance ratio for moment that's like 0.97, and for deflection, it might be 0.85. Who knows? It just changes from problem to problem. Each problem has different moment demands. Each problem has different deflection requirements. One thing that I can pretty much tell you will universally be true, however, is for building members, more often than not, the shear doesn't matter. For bridges, that's another story. For bridges where you're customizing the size of the web and the flange and whatnot, that shear performance ratio starts to go up because you as the engineer are tweaking the sizes of the flanges and the web and so on and so forth. So just something to keep in mind. All right, let me go back to the presentation, but while I'm doing that, does that make sense? Anybody have any questions about that? Okay, so let's talk about design. How would we go about designing a continuously braced beam? First off, I want to be crystal clear that the design process for a continuously braced beam is not the same for a discretely braced beam. They are very different. That we're going to be using different design aids. We're going to be using a little bit of a different process. There are different parameters that matter, so that's something to keep in mind. But for continuously braced beams, it's actually pretty straightforward. So the first thing we have to do is we have to compute the demand. And what we're going to focus on is the moment. We're not going to focus on the shear because the shear tends to not matter. So we're going to compute the factored moment. One thing that you should do is assume a beam self-weight. So if you're in design land, you are trying to pick a beam to support some loads. All beams must be able to withstand their own self-weight. And if you're in design land, you don't know how much the beam weighs because you don't know what beam you're going to use. And so common assumptions are usually something like 50 pounds per foot, 100 pounds per foot, something like that. Now, here's the thing. There are some engineers in building design land that actually don't bother with assuming a self-weight during the design phase. And the reason why is because the beams, the self-weight tends to not matter as much in design land for building beams as opposed to bridges. I don't recommend that. I recommend that you pick something for two reasons. One, you're going to have to account for the self-weight anyways, so you might as well set that process up, at the beginning. And there is a chance that the self-weight doesn't affect the design too much, but if you don't assume something, you do run the risk of having to iterate more times than you would if you just pick something at the beginning. So in my opinion, there's a practicality about picking a number just to go with it. And sometimes what happens is you assume that the beam weighs 100 pounds per foot, and then you pick a W24 by 76, and you don't have to go back and iterate because the self-weight is heavier, the assumed self-weight is heavier than what you actually picked. So if it'll work. And we might have an example of that today. We'll just see what happens. Now, step 2 is to compute the required moment of inertia based on the deflection limit. So the idea is that after step 2, you're going to have two values for design. You're going to have a required bending capacity, and you're going to have a required stiffness. Again, we look at the shear later. Now, the other thing is just be careful with your units. Don't forget that 1728 conversion factor. So after step 2, you should have two values, a required bending capacity and a required moment of inertia. And the way that this works from a selection standpoint is the first thing that you'll do is you'll go to table 3.2. You'll find that capacity and choose a section. Okay, so table 3.2, you will choose a section based on the bending capacity, based on the moment. Okay, and so we might pick, a W24 by 76. Now, what you can do is you can just go into the table and just look up the section, the bold row that has the, that was the pen. You can just look up the row, the bold row that has a phi MP larger than your MU. And it's really simple because table 3.2 is based off of 50 KSI steel. If you don't have 50 KSI steel, you could still use table 3.2. Instead of going in with the phi and P value, you would just go in with the ZX required value. And you could still do this with 50 KSI as well. It's just a little more cumbersome and really not necessary. That'll become clear again as we get into an example. Now, this step 3, what we're doing is we're selecting a section based off the bending capacity. What we then need to do is check that section's moment of inertia and see if it's going to work there too. See, it's possible that we pick a section based off bending capacity and it doesn't have enough IX. And so we toss that section out and then we go to table 3.3 and select the most economical section based off IX. Now you can skip that step if your section off of step 3 is good enough. But if not, then you need to pick another section, and that's the one you're going to go with. Again, really easy, but it'll become clear when we do an example today. Once you're done, though, and you have a trial shape, I think you ought to analyze it. Check the moment capacity, check the shear capacity, check the deflection capacity. The deflection capacity is probably not all that necessary, assuming you did all of your math correctly, because there's really no chance of needing to iterate that, especially if it's just a live load deflection limit. But I still think it's a good idea, especially when you all are starting out, just to make sure you don't have any calculator errors. I don't see any problem with checking the math on a beam that might be holding up thousands of pounds. Take a few more minutes to do it. The only other thing I want to talk about are deflections. And if there's any one suggestion I would have for the steel manual in the future, it would be on this area. So I want to bring it back to concrete design for those of you that had me for CE 413. One of the things that the concrete spec does really well, I'm actually going to grab a version of the concrete spec. I have an old one right here that I'm going to use. This is, I let another faculty borrow one of my newer versions, but this is the concrete spec. This is ACI. This, like I said, this is an older version. But if I open up the spec and I go to the section on serviceability, which is on, I think, in this section, 126, right here, you know, the spec does a really good job of listing permissible deflections. They're right here. It says maximum permissible deflections for a beam. The ACI spec does a really good job of delineating to the engineer. It says, you know, flat roofs, supporting elements, attached to non-structural elements likely to be damaged by large deflections or not likely to be damaged. Here's the deflection. Here's the limit. It's right there. If you had me for reinforced concrete design, we used these limits, you know, pretty, we use them pretty religiously because that's what the spec tells you to do. Now, that's the concrete spec. Here's what the steel spec says. So if you open up Chapter L is the chapter on serviceability. And this is what it says. It says, deflections in structural members and structural systems shall be limited to so as not to impair the serviceability of the structure. And that's it. It does not tell you what the deflection limits are. It just tells you that you as the engineer need to account for them. And it's one thing I wish that would be sort of delineated in future manuals, that the industry would sort of put that in there. There are reasons for not doing it. And I respect that. I think it would make your lives a little easier. Now, one of the things that AISC I think does do quite well is they do a good job of making your life easier as an engineer if you're designing some funky stuff. There's a lot of design guides that are available for download on the AISC website. And as students, you all can get a student membership for free and download all of these for free. And if you had to pay for these as a practicing engineer, they're like thousands of dollars. So I just recommend doing it just on principle. But they number the design guide. So for instance, design guide 9 is the one for torsion, if you haven't remembered this being twisted. Design guide 3 is the one on serviceability, and it lists serviceability design considerations that you should consider. And most engineers just end up going with these. So for instance, if you remember, we had talked about like plastered ceilings, and we said that the deflection limit might be L over 360, or, you know, maybe for a non-plastered ceiling, maybe, you know, the floor beam, you know, maybe, you know, something like that or whatnot. What I'm gonna do for you all for the purposes of this class is I'm just gonna give you the deflection limits, much like a client would. And in practice, one of two things is going to happen. Either the client is going to spec that out to you, or maybe the architect. If you're the sub on a project, if you're the structural engineer that's subbing to the architect, you know, will work with you on that. And if not, then you're probably just going to go off of something like this anyway. So the limits that we'll use will be of that same flavor, just so that you're kind of aware of that when you go into the field. All right, I'm going to stop or shut up for a quick second and see if anybody has any questions before we do a full-blown design example, start to finish. While you all are chewing on that, I'm going to get something ready. I want to get ready to copy and paste something in my notes here in a second. Anybody have any questions? You should. I mean, there's a lot of them, and they're for some really good stuff that if you've taken a course in basic steel design, we're not going to cover all of this, but some of it is stuff that would really help you out. For example, we covered column design, right? But we did not cover the design of tube columns that are filled with concrete. You know, that's an application that happens in the field, and there's a design guide devoted to that, to, you know, columns encased in concrete. And it's not hard, and you know, if you've had a basic course in steel design, you can walk through it. But they're really good resources because they walk you through, you know, all these different examples, and there's a lot. I mean, it's really good stuff. I think it's worth a download. Okay, all right. So this is our example that we're going to do today. This is a continuously braced beam. It's 50 KSI steel. We're going to assume a self weight of 50 pounds per foot. So this dead load that you see right here, this 1.2 kips per foot does not account for the self weight, okay? For this design, we're gonna ensure that the beam meets a live load deflection limit of L/600. And so we're going to use that to compute the, to limit our design. So let me just get right into it. Now, the first thing that we're going to need to do is we're going to need to determine MU. Now, because I want to be crystal clear, I really only care right now about MU, but because I'm doing the structural analysis anyways, I'm going to go ahead and also compute VU, just because I'm doing this stuff anyway, so I might as well do it all. Now I have a simply supported beam, and it is subjected to a uniformly distributed dead load, but the live load is a point load, okay? So we're gonna have to handle those separately, all right? So let's see, I had pulled my, my manual out here to have this at the ready. So the first thing I want to do is look at this. So this is our distributed load case from the manual. And so I have a beam that is 35 foot long. So this is simply supported. Has a distributed load on it. And it has a dead load of 1.2 kips per foot, but it also has an assumed self weight of 50 pounds per foot, or 0.05 kips per foot. And what I'll say is that is assumed. Okay, that is assumed. And I want to be clear on that because there is a possibility that we need to adjust that later. We might be picking a value. We're going to need to adjust these moments accordingly. That'll become clear in a bit. Now the beam was 35 feet long. So what I'm doing is I'm going off of my maximum shear, my maximum moment, and I'm saying that shear dead is WL/2. Which is going to be 1.25 kips per foot times 35 feet over 2. And the bending moment is WL squared over 8. All right. So let's see. This is 21.875. Somebody check me on that though and make sure I'm doing this. Make sure I'm not I don't have a typo. All right, and then I've got 191.41 foot kips. Am I good on that one? While you're doing that, I'm going to highlight my next one. Okay. Now, I want to be, again, clear. This is based on an assumed self-weight. So if my beam is heavier or lighter, I'm going to have to go back to this and see if this makes sense. Okay. So now we need to consider these live loads. Let me snap this. Now again, everything I'm doing here, I'm just doing shortcuts from what I did in structural analysis. You know, you can always go back to structural analysis and do all this stuff by hand. So for the live load, I have a beam and I have a point load at midspan, and that point load at midspan is 40 kips. So I have a 40 kip load, and this is, you know, 17.5 feet, 17.5 feet, and this is 35 feet. Now, I want to be clear, okay? If you try and take this and you try and turn it into this, you try and say, well, let's just take that and spread it out. And let's say it's 1.14 kips per foot, you know, over a 35-foot, you know, beam. If you try and do that, that is wrong, okay? Because think about what we're computing. We're computing bending moments, okay? And if we're computing bending moments, what's going to be a worse scenario? Lumping 40,000 pounds right in the middle of the beam or spreading it out? Spreading it out, sure, yeah, if you spread it out, you get to use WL squared over 8. But that is an unconservative design. That would result in an unsafe design, so you can't do that. There's 40,000 pounds in the middle of this beam. Analyze it as if there's 40,000 pounds in the middle of the beam. And so what we're going to do is use our shear and max moment. So our live load shear is going to be, is going to be P over 2. So that's 40 kips over 2, which is 20 kips. And then the moment is PL over 4. And just so everybody is clear on where these magic formulas are coming from, you know, if I have a beam that has a load on top of it, and I have a reaction right here and a reaction right here, I'm just going to cut it in half, right? So, you know, if this dimension is L over 2, right? What's the shear diagram look like? I go up, over, down, over, up. So that's P over 2 minus P over 2. What's that area? P over 2 times L over 2, PL over 4 minus PL over 4. Constant shear means linear moment, PL over 4. So I don't want you to think these are like magic formulas. It's just everything we did in structural analysis just done in, you know, in symbol format and then reported to us for each case. Does that make sense? Okay. All right. So now I've got a dead load and live load shear and a dead load and live load moment. So now I can start factoring. And so let's go ahead and do that. So VU is 1.2 V dead plus 1.6 V live. So 1.2 times, what is that, 21.875. Sorry if I'm scrolling up and down a lot. And then MU is 1.2 M dead plus 1.6 M live, 1.2 times, and that was 191.41 foot kips plus 1.6 times 350. So, got ahead of myself. Somebody tell me the VU and somebody tell me the MU. We'll make y'all Do some calcs this Wednesday morning. Anybody got a VU? VU is 58.25. Okay, and MU 789.7. Boom. Okay. There you go. Exactly right. Good job. That's not hard, right? Anybody have any questions about that process? I think that's probably one of the hardest parts of beam design. It's not the design, it's all the structural analysis. Everybody good? Okay. All right. So step 2 is to compute the required IX. Okay. Now, here's the case according to the manual, and the maximum deflection. I'll sort of rewrite it here. It's right there. I'm just blowing it up a bit. Is PL cubed over 48 EI. Is my sound? Am I going out? You might want to log out and log back on, Mr. Riggs. Is anybody else having any sound issues? Everything looks fine to me. Here, I'll type that in. Okay. Yeah, I'm sitting here saying, that's a good point. I was sitting here saying, you might want to log out. And he's like, you can't hear me. It's a good point. Sorry about that. Okay. So, so going back to this, so here's the formula for maximum deflection. And we also know from the problem statement that our deflection limit is L over, and what was it? I think it was it 400? 600. Okay. So let's take these one at a time, okay? And let's chug through this, carefully. I'm sorry. I'll have the recording uploaded as expeditiously as possible. So and that's an idea as well, as Mr. Guy said. Okay, so first off, let's look at the limit. So the limit is L over 600. So that is 35 feet over 600, and this needs to be multiplied by 12 inches per foot. So that ends up equaling 35 times 12 divided by 600 is 0.7 inches. So we're not going to let the beam deflect more than 0.7 inches. So, about like that. All right. Now, for the actual deflection, the live load deflection, we'll call it delta LL max. Let's see how we would compute that, okay? So remember, for this beam, we have a live load of 40 kips. We have a span length of 35 feet, and we have an E value of what? Boom. I want that number burned into the back of your head. For steel, it's just for structural steel, you can set your watch by that. For concrete, you have to compute it based off of your compressive strength, but that's a different class. Okay, so we're going to have PL L cubed over 48 EI. Now, the way that we're going to compute that is we're going to say 40 kips times 35 feet over 48 times 29,000 times, or sorry, whoop, I forgot my units there. KSI times IX. Now, the one thing I forgot here is I have to include my unit conversion, 1728 inches cubed over feet cubed. All right. So now what I've got is I've got two expressions. What I'm going to do is take those expressions, set them equal to one another, and solve for IX. And I'll do that down here. And I'll now that I've got my units accounted for, I'll sort of do it, just in red ink. So 0.7 equals 40, 35, 1728 over 48, 29,000 IX. And so all I need to do is multiply both sides by IX. So, if I multiply this by IX, multiply this by IX, that cancels, and then divide both sides by 0.7. So it's actually pretty simple. All I got to do is swap out the IX and the 0.7, and I get that IX is 40, 35, 1728, 48, 29,000, 0.7. And so IX required is going to be what? It's going to be I'm sorry, I forgot. It's 35 cubed. This is 35 cubed. I forgot that. Nobody caught me on that. It's 35 cubed. I was sitting there putting it in my calculator. I was like, this doesn't feel right. All right, I have a value. I want to see what you're getting. All right, that's what I'm getting. I'm getting 3041 point, we'll say 0.4 inches to the fourth. Okay. Remember, a moment of inertia is in inches to the fourth. Okay. So what we really care about is, remember, at the end of step 2, we have two values that we care about, okay? So I'll say two values. MU is, I think it was 789.7 foot kips. And IX required is 3041.4 inches to the fourth. I swear that's probably the hardest part, getting to that point for this whole process. All right. Okay. Now here's what I want you to do. I want you to select a trial section . Based off MU, okay? And so what that means is this. We're going to open up our table, our manuals, table 3.2, and remember, this is a continuously braced beam. So for a continuously braced beam, the capacity is phi MP. So we're going to go off our phi MP column. We're going to find 789, and we're going to find the lightest section that we can that can withstand a 789.7 foot kips. What section is that? We're just going to do it one step at a time. I want to make sure everybody's following along with what I'm doing. I'm going off the phi MP column because this is, you know, a continuously braced beam. I will here in a second. I will here in a second. You'll see what I mean when I say trial section. But let's just bear with me one step at a time. What's the lightest section that has a capacity larger than 789? No. Okay. But what? All right. Now that's not both. So both Mr. Geis and Ms. Hudson selected within that group, but within that group, is that the lightest section? And you know what I mean by the lightest section, the second number. So, for instance, the one that Ms. Hudson put out, that's it weighs 136 pounds per foot. Mr. Geis's weighs 97 pounds per foot. So between those two, Mr. Geis's is lighter. But is there another section that's even lighter? Remember, we're going off the bold row. There we go. There we go. So let's say a W24 by 84. Now, what is the phi MP for a W24 by 84? It's 840. So it has enough capacity to withstand that load. Now, Mr. Enot asks, can you explain what I mean by a trial section? Mr. Enot, what is the moment of inertia for a W24 by 84? And while Mr. Enot's looking this up, does anybody have any questions? Because I feel like we're going a little slow on this. And I mean, turn your mics on if you have a question, because I want to make sure that you all are following along with what I'm doing here. (2,370 inches to the fourth). What's the problem with that? There you go. That's what I meant by trial section. So we selected a section based off the required bending capacity, and it's got enough bending capacity, but it doesn't have enough stiffness, okay? That's what I mean by trial section. So the W24 by 84 is not going to work, okay? So now I want you to go to table 3.3. Okay, and our IX required was 3041. All right. So help me out there. So what section are we going to use there? Is everybody with me on this? Any questions? Because y'all... okay, all right, again, okay, so this is what I'm talking about. Okay, so the W18 by 158 has the 3060, that you're saying. But why not use the bold row? There you go. But what's the bold row? The bold row is a W30 by 90. It only weighs 90 pounds per foot. The W18 by 158 weighs 158 pounds per foot. Does that make sense? Is everybody else clear on that? Because everybody's kind of quiet today. I want to make sure that you're understanding this. Okay, so the W30 by 90, it's because the flanges and the webs are thick. That's why. So the moment of inertia here is 3610. Now, here's the kicker. Go back to table 3.2 and see if you can tell me what phi and p is for that section. Is it going to work for capacity as well? I know we're running short on time. I'm going to have to finish this example in a separate video. But I want to answer this question. And then we'll call it. It's on page 3-24. All right, 1060 foot kips. Is that enough? Well, the short answer, and I'm going to finish this in a quick video. The short answer is it should be enough, but this W30 by 90 is heavier than what we assumed up here because we assumed 50 pounds per foot, and this beam is 90 pounds per foot. So it should be good, but we're going to check it just to make sure. Does anybody have any questions about this? Because I'm getting in my video, I'm going to make sure that I pull up the manual so that you all see where I'm pulling these values, because I get the feeling some of you might be losing me on the manual here. But any other questions before we call it? Well, there's just more steps. I will clear up some of the table stuff in a video that I'm going to post actually like right now. But we're running out of time, so I'm going to go ahead and call it. Just be on the lookout on my playlist. I'll clear up some of the issues here. One final thing: if you all have any questions, you can turn your mics on and ask. Make sure that you're getting your money's worth on class. But that's all I have today. I will see you all on Friday.